Hello class, I hope you're enjoying your day off. Here we are back for example number 2 in our arc length adventures. And I should probably shut my door so I'm not annoying everybody down the hall. And let's see, I move myself over here. Okay, so for this example, our parametric curve has equations x equals t squared, y equals 4t cubed minus 1, and we're looking at t ranging from -1 to 1. Here, we will again be applying our formula for arc length, and as we know, that is, let's see, oh, it went ahead. Let's go back. There we are. Okay. So the length is going to be equal to the integral. In this case, it'll be from -1 to 1, square root of dx over dt squared plus dy over dt squared dt. Okay, now of course to do this we have to know what our derivatives are of our parametric equations. Well, in this case, they are relatively easy to do. dx over dt is just going to be 2t. Let's see, erase 2t, and then dy over dt. Similarly easy, it will be 8t squared. No, 12t squared. There we go. Okay, so we'll put those in. And let's see, should we square them right away? Why not? So 2t is going to go in for dx over dt. Squaring that, we're going to have 4t squared. And then with our dy over dt, we'll square that as well. 12 squared is 144. And t squared will be t to the 4th dt. Okay, and I think I've mentioned many of these integrals turn out to be very, very hard to do, maybe cannot even be done by sort of standard techniques. And I think you can see how that might happen, but with this one, it actually does turn out to have some nice simplification to it. So one thing we notice right away is that there's a common factor of 4, and there is a common factor of t squared. So we can pull both of those out. Now, here we do actually have the issue of plus minus, because t could be negative, but we can do away with that pretty easily, and we can do that with multiplying by 2 and integrating from 0 to 1, and we can do that because our integrand in this case is even. Okay, so we have that property, that symmetric property of integrals that says we can do that. Okay, and let's see. Now that we have written it that way, well, okay, so let's pull out this 4t squared, and we'll see that what is left is t squared plus, let's see, maybe 36. 36t squared. Actually, in the first term, we pulled out the t squared. So if I can remember where the eraser is, we'll put a 1 in for that. There we go. And we got dt. Okay, so now let's go ahead and square root the common factor that we pulled out. And we'll get 2t for that. Now that we are assured t is non-negative. And with that 2, we could pull it all the way out and give ourselves 4 in front of the integral. T better stay inside. And then we got square root of 1 plus 36t squared. So square root with a bunch of stuff in, Ordinarily, that could pose some difficulties for integrating. But here, that t that ended up outside turns out to be just what the doctor ordered for doing this integral, because now we can do a substitution, right? We could set u to be what's inside the square root, which is 1 plus 36t squared. du now, in this case, is going to be 72t dt. And if we just divide the 72 over, du over 72 equals t dt, and that's exactly the leftover factor that we see in our integrand there, aside from the square root. If we go the route of changing our variables all the way, let's do it that way again. And you got some options here, but we'll stick with that method here, that tactic. So when t equals 0, u will equal 1. And when, lost a bit of my w there, when t equals 1, u will actually equal 37, strangely enough. Okay, so doing our substitution then, we can pull out that 1 over 72. Now it's going to be 4 over 72 out front. Integral now is going to be from 1 to 37. And then our integrand will just be square root of u du. And you know, square root of u, that's u to the 1/2. So when we anti-differentiate, just use our power rule for antiderivatives, get u to the 3/2 times 2/3. Kind of a lot of constants out here. Let's see, this is going to be 1 over 18, I think. And then we've got u to the 3/2. Ooh, I'm going to squeeze a 2/3 in here. And then we're going to evaluate at 137. 37 first, of course. And let's see how that shakes out. So if we multiply our fractions together, 2 cancels with the factor of 2 in the 18. We get 1 over 9 times 3, which is 1 over 27. And then we're going to have 37 to the 2/3 minus 3/2. Oh, let's see. That does kind of make a difference too. 3/2. And then 1 to the 3/2, of course, is just 1. 3/2, you could, rewrite it with a square root in there, but no big deal. Now, this is an important stage because this is our exact answer. This is what we really want to get. Although it can also be enlightening to look at a decimal approximation as well, as long as you have the exact answer in there. So if we do a decimal approximation on this with a calculator or so forth, we will get that this is about 8.299. And you might wonder, well, how do I know whether my answer is reasonable? Okay, we did a lot of computations, a lot of complication involved there. Is this a answer that could be right? Well, one way to check that is by looking at a graph. So let's take a look at that. Let's see if I can. How do I do this? Yeah, move myself over here now. Okay. So if we look at a graph of this, what we find is that it's actually not too far from being a vertical line. Okay, so come on, there we go. There's my y-axis, and then the x-axis we'll put right about here. What we find is that the initial point of this curve is at 1, -5. So down here, pretty sure that's the initial point. Let's double check it. When t is -1, -4 minus 1 is indeed -5. Yep. So from 1, -5, it then kind of meanders over here to the x-axis, bounces off, or the y-axis I should say, bounces off of the y-axis at -1, continues on up here to its terminal point, which is here at 1, 3. Okay, so what would be reasonable here? What would be an estimate for this? Well, let's see if, just get something a little different here. Let's go to red. Okay. What we could do is we could just put a vertical line in here, and it's really easy to see that that vertical line has length 8. Okay, now 8's a decent estimate for the length of our curve. It should be an underestimate because, of course, if we take a little detour over there to the y-axis and then come back, we're going to be lengthening our path a little bit, but not drastically, right? Most of this is the vertical change, and then it's just that little horizontal bop over there to the y-axis. So our answer is definitely consistent with that. 8.299 is indeed a little bit greater than 8, which is what we figured should be our fairly tight underestimate. So, yay, we found the length of another arc. One more to go. We'll see you at example 3.